In this video, we'll compute pi using only whole number arithmetic. This video will describe a base 10 spigot algorithm for calculating pi. The algorithm is in base 10 since digits are in the usual base 10 radix system. A spigot algorithm is one where the digits are computed one by one and can be discarded immediately after they are computed. This method was described in 1995 by two mathematicians. To do this type of spigot algorithm where we use only whole number digits, we need to have an expression for pi that can store those digits successfully. There's an expression for pi which converges at a rate of about 1 bit per term, and this is well known. It's equal to 2 plus 1/3 times the quantity 2 plus 2/5 times the quantity 2 plus 3/7, and it keeps going in the obvious pattern. To calculate the decimal digits of pi, we need to convert these fractions into expressions of the form shown here. So we can read off the digits 3, 1, 4, 1, 5, 9, 2 when we calculate pi in this way, and then those are saved or discarded. We can keep track of the digits of pi in a spreadsheet. In order to calculate the digits of pi and store them in a spreadsheet, we need to know the dimensions of the spreadsheet, which can be determined ahead of time. According to the authors of the original spigot paper, if we want to compute n digits of pi, then we'll need to use d columns, where d is equal to floor 10/3 n. Here's an example of a type of table which can be used to compute the digits of pi. In the B column, we'll see the digits 3, 1, 4, 1, 5, 9, 2, which correspond to the digits of pi. In row 1, we get the numerator of the fractions. In row 2, we get the denominator of the fractions. In row 3, we get the starting entries, which are 2. And then the remaining computations will convert the initial fractions to the final fractions. The spreadsheet on the previous page computes digits of pi down the left side. The only operations used in this schematic are addition, multiplication, division, floor, and modulo. The operations in this spreadsheet perform a change of basis. On the next slide, we'll show the formulas in the upper left submatrix. This slide shows the formulas from which the numerical matrix on the previous two slides where it came from. You can see that in column B, we get digits of pi. Columns C through onward have a very regular pattern in terms of their formula. The formula is periodic. We have to note that for this to work correctly, there's only a finite number of rows and columns inside the matrix. In order to initialize the data correctly, we need to put zeros into the rightmost non-zero column with corresponding to the carries. Additionally, we have to be careful about running into digits which are more than 10. The only valid digits in a decimal number are 0 through 9. If the digit is computed as 10, then we have to carry that 1. There's a more rigorous computation shown with the code that follows this code. One of the bad things about having a spreadsheet to compute the digits of pi is that we have to recreate the whole table if we want to memorize what the intermediate calculations are. We need to store the intermediate calculations. Instead of using a spreadsheet to compute the digits of pi, we can do something a little bit more clever, and that is to use a dynamic array instead of a matrix. Using this array, we'll be able to save a lot of memory. This array is named M. M corresponds to matrix, but we're only keeping track of one row of the matrix at a time. There are a few other counters that we need to analyze the digits as they come out. The important code on this slide is to initialize the vector. This vector will contain a bunch of 2's that correspond to the digits of the nested fractions. The next part of the code is a for loop. The for loop will help us go through row by row what the quotient and remainder of the data is. We can use a switch statement to branch on printing out code based on the digits of the quotient, where the quotient will be computed later. Then at the very end of the code, we'll print out the last digit D. Next, we'll get to the heart of the code. We want to update rows in our matrix, and then sort them in a vector, each row in a vector, which the vector will be overwritten as many times as we need to. We also will supply C, which is the number of columns, and Q, which is the quotient. This is essentially doing a change of basis from the original the original nested fractions to the trivial nested fractions. Now let's create 2 helper methods. The first helper method will print repeated copies of a single digit. The other helper method will change the matrix and initialize it to a bunch of 2's. The last bit of code is parsing the command line arguments. So we want to have the user use the code as Java space pi space number of digits. The preceding code on the slides was tested and it works to compute pi up to at least 200 digits. Further increases may overflow the matrices and vectors since they are bounded from above. If you liked this video, be sure to like, comment, and subscribe. Tune in next time for more STEM content.